Welcome to the Phenomenological Alliance channel. In this video, we will discuss the contextual aspects of the laws of nature.
The question of gravity, concerning why heavy objects fall toward the center of the Earth, is an age-old question. Aristotelian physics is based on the recognition of four distinct spheres or elements in nature. Today's understanding of the four states of matter, solid, liquid, gas, and plasma, originates from these early concepts. Essentially, Aristotelian physics divided nature into the lithosphere, hydrosphere, atmosphere, and thermosphere. Beyond these terrestrial spheres, there is a celestial realm filled with ethereal substances, referred to as the fifth element. In these celestial spheres, planets are propelled by ether. The elements tend to their natural place. Heavy bodies fall toward the center of the Earth, while light bodies rise away from the center, as observed when cinders are lifted by fire or in flying lanterns. In these contexts, Archimedes' principle was presented as a realistic depiction of these phenomena. However, in antiquity, various philosophical schools existed, and the strongest opponents of Aristotelian philosophy were the atomists. According to the atomists, nature is composed not of four elements, but of atoms and their motions. In the 1st century AD, the Roman philosopher Lucretius, in his poem On the Nature of Things, argued that natural motion is solely downward, because no force can propel atoms away from the Earth's sphere. Despite criticism, the concepts of Aristotelian physics endured until the Renaissance. However, the acceptance of the heliocentric cosmological model initiated the rejection of all Aristotelian concepts. In the 17th century, the renowned English physicist Newton formulated the laws of mechanics and applied them to cosmological questions. Discontented with the cosmic vortex theory, which posits the existence of invisible forces in the vacuum, Newton proposed that the downward force attracting the apple to the Earth also keeps the Moon in its orbit around the Earth. Newton proposed a gravitational cosmological model wherein planets move by inertia, devoid of a propelling force. Within this model, centrifugal force is seen as a reactive force governed by action and reaction, rather than being attributed to a specific physical cause. This directly stems from the conviction that natural motion occurs only as downward motion. The Moon's trajectory curves under the influence of gravity, a concept introduced by Newton through mathematical calculations. Newton's model left the physical cause of gravity unexplained. As it acts not through contact, but rather mechanically at a distance, the idea emerges that gravity represents a force field, a region of space with special properties. Following Newton, numerous attempts were made to elucidate the gravitational field, though none gained widespread acceptance until the advent of Albert Einstein. At the outset of the 20th century, Einstein spotted a similarity between inertia and gravity through a thought experiment. Imagine a person in a hypothetical elevator moving with constant acceleration in deep space. He would not discern whether he were on Earth or in space, for in both circumstances, the descent of a ball would remain identical. Given the universality of free fall, there's no observable difference between inertial motion and motion under gravitational force. Objects move similarly under both conditions, following natural, unforced paths. As motion defines the geometry of space and time, Einstein inferred that gravitational motion results from the curvature of spacetime. Inertia arises from mass in motion, while gravity stems from mass curving spacetime.
Let us conduct a phenomenological analysis of the mentioned axioms. Einstein overlooked the fact that if an imaginary person in an imaginary space elevator accelerating constantly, we are holding a real helium balloon, the balloon will tilt in the same direction of the acceleration. The universality of free fall is a declaration made by Lucretius to justify the atomistic concepts. Free fall always has its counterpart in free buoyancy, as these phenomena always occur together. While it is true that a person in an imaginary space elevator might not initially know whether he is on Earth, constant acceleration is not a realistic scenario. In the real world, a person begins and ends acceleration at specific moments. Once the constant acceleration ceases, the person will sense it due to detecting changes in acceleration through his sense of balance. Einstein's argument, which led to the development of the concept of curved space, is based on an assumption that contradicts fundamental physics principles. Maintaining constant acceleration is not possible. Einstein's insight that inertial and gravitational forces share similarities in appearance suggests that inertial gravitational forces manifest in motion, not at rest. Frictional reactive forces, like all other reactive forces, only exist when there is motion. Centrifugal force is present exclusively in curvilinear motion. All reactive forces, including gravity, result from motion that causes instability. To understand the nature of these forces, we must explore the relationship between stability and motion. In previous videos, it was demonstrated that motion causes imbalance. When a body is accelerating, it either moves with the acceleration or against it. Balance is achieved in uniform rectilinear motion. In circular motion, there is a constant imbalance. On a merry-go-round, one must grip the handrail to avoid falling. A stationary object will fall off a spinning turntable. A penny on the turntable will be pushed to the edge. Yet, in a double rotation system, the equilibrium disrupted by curvilinear motion can be restored. While it is impossible to manually rotate the rotary disk, if the disk begins to spin, it can be rotated along a certain axis of rotation due to balancing forces. Placing a ball on the rotating disk, the dual rotating system generates dynamic stability. Once the ball reaches a stable rotation, it synchronizes with the disk's rotation. The people inside the spaceship remain in a balanced state because of synchronized motion. However, when subjected to acceleration in unsynchronized motion, they start to perceive weight again due to so-called artificial gravity. In the same manner, artificial buoyancy is generated. In circular motion, the centrifugal force drives the pendulum away from the center of rotation. However, in a double rotation system, the pendulum regains equilibrium if the rotational speeds are synchronized. In circular motion without synchronization, centrifugal force drives heavier objects to the periphery. A rotating marble in a plastic ball is forced outward against the axis of rotation. However, in a dual rotation system, synchronization can arise, restoring balance. During synchronized motion, the marble returns to its equilibrium position. In the same way, equilibrium points appear in the solar system's complex rotational dynamics. Due to Earth's movement, this point is at the center of the Earth. Objects on the surface of a celestial body experience imbalance and strive to restore balance. The Earth's spheres are ordered from heavier to lighter. Newton's analysis failed to acknowledge that acceleration represents a state of imbalance. In the 17th century, when it was commonly believed that humans had only 5 senses, Newton approached the problem of free fall within the limitations of his time. Limited by the contextual understanding of his era, he relied on the sense of sight, through which acceleration is perceived as a change in speed rather than a state of imbalance. Through visual perception, we overlook that the apple is part of a synchronized rotating system, leading us to attribute the balance we feel, even as the Earth rotates, to an enigmatic gravitational acceleration. As a result, Newton was led to assume the existence of a static force pulling the apple toward the ground. Yet, gravitational force, like all other reactive forces, manifests in motion, establishing balance in synchronous periodic motion. Being part of multiple rotational system, the apple's imbalance is maintained by physical contact through the stem. Once this contact ceases, the apple reverts to balance. Likewise, when the rope snaps, the helium balloon that was tied to a branch regains its equilibrium. Any object with a specific angular velocity will seek to reach equilibrium. For massive objects, equilibrium is located at the stationary orbital trajectory. In the Sun-Earth system, the equilibrium is at the Earth's center. Within a double rotation system, the existence of force causing the balance restoration should not be sought outside the body, but within it. In multiple rotation systems, stationary orbital trajectories are formed around the central balance point. Cavendish's experiment cannot be taken as a conclusive proof that the attraction between masses exists. The pendulum's oscillations are not caused by the lead balls. Even in the absence of lead balls, deviations occur due to the Earth's rotation. A phenomenological perspective suggests that gravity is neither an action at a distance nor an external field. Rather, it is a force that arises during the process of balance restoration in the synchronized motion of multiple rotational systems.
Phenomenology examines the way things appear in our consciousness, experienced from a first-person perspective. Consciousness does not exist without content. It is always consciousness of something, be it an external object, or our internal state, or interactions between objects or individuals in the widest possible sense. The content of consciousness is always governed by our intentions to be aware of the content. Such an insight was a foothold for the development of the concept of intentionality. It describes the process through which we become aware of internal and external phenomena. The application of phenomenology in physics raises awareness of phenomena and prompts the revision of generally accepted principles. As these principles are viewed as laws of nature, their modification is restricted by contextual factors. However, the only constant in phenomena is the reality of their appearance, not our contextual interpretations of that reality. The fact that the apple falls from the tree will not change. Our understanding of why the apple falls is always subject to revision and change. The pace of development in the natural sciences is conditioned by the capacity to accept and adapt to ever-changing contexts.